is also, especially in smooth muscle, measurable. So the general rule applies. We have the majority of resting potential created by potassium leaving the cell and leaving the negative ions behind. That's why we have negativity. But we also have some contribution from sodium-potassium ATPase. Remember how it works? Throws out 3 sodium, brings in 2 potassium. 3 minus 2, 1. 1 positive charge leaves the cell, which means some hyperpolarization inside. Okay, so this is summing up with resting potential created by potassium ions, and we have more negative potential in cardiac myocytes and in skeletal muscle, somewhere around minus 90 as opposed to minus 60, 70 in neurons. In skeletal, in smooth muscle, we have a huge variety of values, ranging from minus 40 to minus 70, minus 80, so these are much more diverse. We'll come to that in a second. But now let's progress to the upstroke reduction potential phase 0. What current plays the major role? Like in neurons, voltage-gated sodium channels. So if myocyte is depolarized to threshold for these channels, they start to open. And they carry inward current. Sodium rushes into the cell, creates inward current, depolarizing current. That has 2 consequences: rapid depolarization. So membrane potential now approaches sodium reversal potential, positive values. And the second consequence, near membrane concentration of sodium ions slightly increases. Although current is quite big, it's very short. So the total amount of sodium that enters the cell is not that great. But because it diffuses relatively slowly, just near the membrane, we have good concentration of sodium rising. And then it decreases because of diffusion, and because of sodium-potassium ATPase removes it, and because of sodium-calcium exchanger working, as we come to it in due course. This is followed by a short phase of partial repolarization. Phase 1. In some animal cardiac myocytes, this is absent. For example, in guinea pigs, the plateau starts from here and goes without initial repolarization. But in humans, we have that rapid repolarization, so we need to know what the mechanism is. And in rabbit heart, which is pretty much similar to human heart in terms of action potential, we also have this. And these are due to the activation of potassium channels, voltage-gated potassium channels, but not the usual non-inactivating ones. Potassium channels that can activate rapidly, much faster than neuronal potassium channels. And they also inactivate. So they can only provide transient outward current and sodium current during this type inactivates due to inactivation in sodium channels. So at that brief moment of time, we have a balance of 2 currents, inward and outward, shifted in favor of outward current. So there is a partial repolarization. But what happens to these channels? Potassium channels, they inactivate. So they can't provide full repolarization. And by this time, there is an activation of voltage-gated calcium channels. These channels activate slower compared to potassium and sodium channels, these potassium channels and sodium channels. So the peak of outward current decreases because of inactivation, and there is an increase in inward current, so calcium channels. And the balance of these 2 currents will dictate the phase 2. If they balance each other precisely, the plateau will go flat, parallel to the time line, no change. if sodium current, potassium current is slightly more than calcium current, there will be slow repolarization, like this. If for whatever reason these channels inactivate slower than usual, or if you have activation of another group of potassium channels, this may go even up. That's what happens in rapid heart. Subtle differences, but they are all due to precise balance between inward currents and outward potassium currents. Inward currents are carried through L-type calcium channels, and sodium channels by that time are all inactivated under normal conditions. Sometimes due to mutations in sodium channels or due to abnormal phosphorylation of sodium channels, they may not completely inactivate, and that will create problems for cardiac muscle. And we will come to that in a couple of years' time when we will be talking about arrhythmias. But for now, just let's remember that normally, in normal heart, you have full inactivation of sodium channels, partial inactivation of outward current through inactivation of subpopulation of potassium channels, and activation of calcium channels, L-type calcium channels. As time progresses during the plateau, there is an additional activation of voltage-gated potassium channels, non-inactivating. So one group inactivates, another slowly activates, and by the end, some calcium channels also inactivate. Very few of them. The inactivation is very slow, but it's there. So eventually, the balance between inward calcium current and outward potassium current again is shifted in favor of potassium current. So potassium channels are prevalent at that stage, and membrane potential moves towards resting potential, towards the potassium equilibrium potential. And that is responsible for phase 3. So potassium channels, they called delayed rectifier because the activation is slow, delayed. They activate and bring the membrane potential, transmembrane potential to resting level. Calcium channels partially inactivate, partially deactivate. If you don't have depolarization, the channels will close because they open when there is depolarization. Okay, so during all this long period, we have several phases changing one into another due to all the currents listed up in the upper part. And these currents compensate each other, balance each other. So the arrows here show which direction is prevalent. Outward in the resting conditions, inward in phase 0, outward in the initial repolarization, phase 1, calcium and potassium balancing each other during plateau, and again potassium prevalent during the last phase, rapid repolarization. Okay, so this is how cardiac myocytes maintain this long action potential. And if you think about it, you will realize this is not a trivial task. What myocytes need to do? They need to have very rapid depolarization. You can't get away with slow up, maintain, and then slow down. Why? Because propagation of cardiac action potential depends on the rapid upstroke, like in neurons. So you need rapid depolarization. Yet you need to maintain that action potential at depolarized level long time despite inactivation of sodium channels. So that's where slowly inactivating calcium channels come into play, and the plateau can be maintained for a long time in coexistence with very fast depolarization. And the whole system has to repolarize reasonably fast to recover sodium channels from inactivation and to prepare for another next action potential. And the system has to be very reliable, because if these action potentials are not generated precisely of the same size, shape, we will die. There will be no pumping of blood. So this is very difficult task, and that's why so many channels are present and functioning in the cardiac muscle. Now, in neurons, short action potential has to be short to ensure propagation of series of action potentials at rapid rate. If action potential is long, the next one cannot be generated, only after the completion of the previous one. Okay? So we need short action potentials. In skeletal muscle, duration of the action potential is not what is important, because we don't need to signal along the muscle. Neurons do that. Neurons regulate muscle. Yet in skeletal muscle we have relatively short action potential, only slightly longer than in neurons, about 5 milliseconds, 3, 5, 7 milliseconds. And these two phases are absolute refractory period and relative refractory period. Now, if you record this action potential, at the same time recording force from the muscle, contraction from the muscle, you will see that contraction starts when repolarization is almost complete. So there is some time delay. And the peak of single twitch, single contraction, happens when the membrane is already in complete recovery. The relative refractory period is over just before the peak of contraction. That means that this muscle can generate a second action potential and trigger second contraction starting from the peak of the previous one. So if command comes from the neuron in fast succession, the muscle will generate strong contraction because of summation of contractions. If it comes somewhere here, the muscle will generate the same contraction as before. And that gives you a huge advantage in terms of regulating the force of contraction. As you imagine, I'm applying the force just to bend my arm much lower than I have to do it to lift a monitor or to lift some device here. How that is implemented? By different frequencies of action potentials from neurons controlling the muscle that has to work. In cardiac muscle, however, the situation is completely different. We don't have a requirement for summation. Quite the opposite. The contractions have to be single twitches to provide pumping, because if you have contractions and then tetanic state for a long time, there will be no proper blood pumping. So we need repetitive phasic contractions. And to achieve that, the refractory period should happen after the peak of contraction. And that's exactly what happens because of long duration of an action potential. So refractory period, relative refractory period, when the muscle, cardiac muscle, can generate second action potential, is very much at the end of force generation. So if another action potential is generated somewhere here, the twitch will be triggered, but that twitch will never summate with this one, at least with the peak. So there might be some increase in the diastolic pressure, but not much. So that's the essence. Why we need long action potential in cardiac myocyte? Why do we need action potential in the first place? To trigger contraction. Why do we need it long? To ensure that the contractions are not summated, they are phasic, they are twitches in cardiac muscle. Okay, if you look